Good morning, Joe.
Good morning. Can you hear me okay?
Yes,
Good.
Hello, can anyone hear my voice?
yes, พี่ครับแบงค์
สวัสดีครับ Hello everyone. Good evening from Thailand. Good evening from Thailand.
maybe we wait a couple more minutes.
สวัสดีค่ะ
สวัสดีครับพี่เปิ้ล
สวัสดีค่ะบริน Hi Hi
Hello.
Joe Hello
Hi
Hi Hi Rina
Good morning, everybody.
Good evening
Or
everybody
evening. It's your evening. I forget. It's your Monday night.
Hello, everyone.
Hi again.
Hi
Hello.
Aganim Today is Thailand Floating Festival. It's a lot of kids go with their families to do the floating.
To do what? What is today?
Floating. We we float whatever that we think is not good for the year to into the river.
Huh.
And we collect the water sample to test.
It's good to
In the
throw the
water
bad
quality.
things into the water.
Yeah,
A
and
lot
then
of bad
we
things will stay.
yes, and bad things stay in the water, and then we need to test it. Yes. We wait for maybe 2 more minutes. Bye. How many people do you expect Buren today, this evening?
I don't know. We haven't got any confirmation. We just announced the meeting.
Is that
Hopefully, the
like,
number should be about the same.
yeah. Are we up to 20? I can, if you want to test how many people will participate, what would be the number?
Honestly, I'm not sure, but
Okay.
I guess the 5 people from our
5
side, I
people.
guess. Yeah.
Okay. 5 people from your side. Okay. Will Darling Joy?
Always seen him.
Have you seen him?
No.
He said he will do his best to join, but it's Monday, so Monday evening probably he's on the way to home or so it's hard to say.
Okay. Okay. Yeah, I think how about we can start in 5 minutes now, after the session time, right? Joe, the floor is yours.
Okay. Good morning, everybody. So today we're going to continue our professional learning on Zoom. I wish I could be there with you, but that's not the way it is. I did send I sent several pieces of material to Buren. I hope that you received it. You should have a PowerPoint, a student worksheet, a lesson plan for today that you could look at tonight, just if you wanted to see where I got the ideas from today. And there was one other thing. Oh, and the video, so that if your colleagues are not with us today, then you can share all this information with them, and they should be fine for picking up where we, learning what we talked about today. So I'm going to share my screen. So today what we're going to do is we're going to engage in explanation. And why are we engaging in explanations today? Well, most of the curriculum that you'll be working with, the water quality unit, the health in our hands unit, and the interactions unit, all have as an essential component of activities that students engage in as explanations. So we're going to sort of learn how to do explanations. I'll introduce you to explanations so that when we do them in the curricula, that you'll have a sense of what's going on. So today's work will just focus on explanation. I think it'll take us through for 2 hours, about, maybe a little sooner, hopefully not any longer. So just because we're going to be together for such for a number of days, the next couple of months, I just wanted you to know a little bit about me. I know that many of you met me during the summer. But it's always think it's important, since we're going to be together for so long. What motivates me? So I've been involved in the teaching profession for many years now, since 1994. I'm sorry, since 1974. Quite a difference there, 20 years. So since 1974, and what's always driven me is how can I provide all students opportunities to learn scientific ideas and habits of minds that will really allow them to live productive and fruitful lives as citizens. And nowadays, because the world's become so global, it all has to do with global citizenship. So just so you know, I've always, from an academic standpoint, when I started as a high school chemistry teacher and through my life as a professor, have always been driven by trying to get kids to really try to provide all kids opportunities to learn. So what will we do today? So we're going to hopefully build some common understanding of how to engage students in scientific explanations. We're actually going to engage in doing some science. You're going to you're going to see some science, and you're actually going to write a scientific explanations. You're going to hopefully I'll answer some questions. And I really want to stress, please ask questions. You could raise your hands on the chat. I think hopefully you know where the hand function is, or if you don't know where the hand function is, just call out. You can also put I'll be monitoring the chat. I'm pretty good at monitoring the chat as I go. And we'll be I'll be trying to answer questions. I see that the materials are on. There's a link to all the materials on your in the chat. If you haven't seen it, you can click on it and download all the information. Okay, we're going to start off with just some basic ideas to begin with. These cut across not only today's session, but again, for the water quality unit that you'll be looking at, the health in our hands unit, and the interactions unit. And the big, science education has really changed tremendously, I have to say, in the last 10 years. And I've been fortunate enough to serve on 3 important committees that all hold the same viewpoint. The first one is the Framework for K-12 Science Education, which came out roughly 10 years ago. In the last couple of years, I've served on PISA 2025. I've recently come off of the National Assessment of Educational Progress in the US. And I also know much of what's going on in China, Germany, in Finland, because I have very close colleagues there. I was really impressed to learn just recently that, in fact, China has actually has now, as part of their fundamental curriculum, built-in project-based learning. So I was really quite happy. So in the last 10 years, science education has really changed. And I think the biggest change is this emphasis on kids as teachers, us really trying to support students to have them develop usable knowledge. What is usable knowledge? It's when students can apply their own scientific knowledge and scientific practices to figure out complex problems or explain real-world phenomena. And of course, that's in some respects, that's always been a goal of education. This is another way of just saying transfer. How can we get kids to really use their knowledge in new situations? So we're really trying to develop this usable knowledge. And this, I have to say, from across the globe, as much as I know, this has really become an important, a really important aspect. Once again, I know it's true in China, Germany, Finland, the US. It's also true on international assessments like PISA on OECD. And so this is the driving point. And one of the reasons why usable knowledge is so critical is because our children are going to grow up in a world that's going to be look very different than today. Just imagine what the world looked like when you were a child, and they're gonna be even in a more technology advanced world. And so we have to equip them with the abilities, with the thinking skills, and the background knowledge to make sense of new situations that arise at all times. And in the US, and actually throughout the world as well, the way to get this accomplished, and this is research-based, is that we have to get students to use disciplinary core ideas, scientific and engineering practices, and cross-cutting concepts. And one of the wonderful things about explanations is when kids write explanations, it's exactly what they're doing. For one, writing a scientific explanation is a practice. And we'll talk more about that later. So three-dimensional learning, this idea of actually using disciplinary ideas, cross-cutting concepts, and scientific engineering practices together, is really a shift of what we see happening in classrooms. And it's through that aspect, it's through using those three dimensions that kids will actually develop that usable knowledge. So just briefly, I think I talked about this in the summer, so let me just briefly say, what are disciplinary core ideas? Think of disciplinary core ideas as the big ideas in science. Ideas like energy, evolution, ecology, those are the big ideas. We really want to get kids to really understand those big ideas. And we want to help them understand those big ideas as they go through their schooling. And one of the reasons why big ideas are so important, if I really understand ecological events, if I really understand gene-environment interaction, if I understand how forces at the molecular level impact the world, then I'm going to actually be able to describe and explain a lot of many of the problems that children will encounter in their daily lives. But from an idea perspective, there are other kind of ideas as well. Those are disciplinary ideas, which means they're basically focused on a discipline. There's also these things called cross-cutting concepts that scientists use all the time. Seldom as educators do we ever bring them to the forefront, but those are ideas like patterns, right? Scientists always look for patterns. It gives us a clue about what's going on. Cause and effect, what is causing one thing, what is the cause of something that happens? Scale, proportion, and quantity. We can look at many phenomena and we can observe them at the macroscopic level, and we can say, okay, what's happening at the microscopic level to actually influence this? Systems and systems models are huge aspects, and we'll be dealing a lot with systems and systems modeling in the next couple of weeks as we get further and further into designing models. So cross-cutting, I love to think of cross-cutting concepts as a way of scientists, remember, it goes across the sciences, of actually having them look at phenomena and make sense of it. And then lastly, there are these things called scientific engineering practices. Many of you are very familiar with these things, right? This is what we used to call the inquiry skills. But nowadays they're switching the world. We now speak of them as scientific practices, partially because there's more of them. So yes, we're still asking questions. Yes, we're still doing investigations, but you will notice that there's other things in here, like developing and using models. I know as a learner, I didn't develop a model until I was in graduate school. Developing explanations and designing solutions, that's another critical aspect. And what's really critical about scientific engineering practices, they're never done in isolation. One practice, you never just do one practice. There's always several practices combined. So hopefully I'll illustrate that today. And what's really critical is these practices actually all work together. Ah, yes. I'm going to stop, and I want everybody to say yay or nay in the chat. Am I speaking too fast? Okay, that's great. I see a lot of nays coming through. I thought I was talking too fast. I'll try to slow down just a little bit so everybody can catch what I'm saying. What's really critical about these is they all work together. So they're the way that scientists figure out the world, and they're the way engineers actually study the design world. And they all work together. And hopefully today I'm going to illustrate that. Practices are different from inquiry. Practices shift the classroom to environment where students are learning about science ideas to explore the world. That's what these practices allow us to do. So they should be tools. You can think of scientific practices almost like tools that we have in the back of our pocket that we're going to pull out and we're going to use. And often when you think of just building or doing if you're a cook, you have tools when you cook. If you're a carpenter, you also have tools. So but you never just use one tool, you always have several tools. The same thing is true of scientific and engineering practices. They're tools that we use to explore the world and make sense of the world and help us build further knowledge. And I know I mentioned this during the summer, but I just want to reemphasize it in that these three disciplinary ideas, knowledge, core ideas, cross-cutting concepts, and scientific and engineering practices all work together. When we, as student scientists, when I'm trying to make sense of some phenomena, I'd never just make use of disciplinary ideas. If I'm trying to figure something out, I have to engage in practices, and I have to use cross-cutting concepts. Those three things work together to allow me to problem solve, which is a critical skill that we want kids to develop going forward. Making decisions, explaining phenomena, and learning more when they have to learn more. So these three ideas, these three types of knowledge, that's what I like to refer to them as, really work together to make us as learners being able to understand and figure out the world. Okay, so that was just some overall background. And one of the reasons I want to sort of review it is, once again, it's going to be fundamental to all of the units that you're going to be exploring. They all involve important disciplinary ideas. You heard Anne speak the other day about water quality. That brings in big ideas related to ecology. The health in our hands focuses on gene environment and interactions. So they all have important disciplinary ideas, but they also engage kids in practices, investigations, designing investigations, asking questions, and of course, explanations, what we're going to focus on today. And so this is one reason why I wanted to go over all these three ideas, because all the units make use of them. And so understanding this notion that if we're really going to help students develop usable knowledge that they can use throughout their lives, then we have to engage them in our classrooms using these three forms of knowledge and having them figure out phenomena and solve problems. Otherwise, we're going to just have learners where we were 30 years ago. But the world is different today. Today, the world is one of knowledge production and making sense of knowledge, and not just knowing something, right? Knowing is important, but it's not the only thing. We have to be able to do. And so what we want our learners to be able to do and use their knowledge. Again, I'm going to remind you, if you have any questions, please put them in the chat. Okay, so what are scientific explanations? Which is the focus of today. Well, if you stop and you just think just for a few seconds, scientific explanations is the core of what science is all about. Science is all about explaining the world. Why do things happen? I think throughout the world, we have, you're going to be your nighttime. You're going to see a beautiful full moon. Why do we see full moons? That's a phenomena. And it's a gorgeous full moon this time of year. I can't see it out my window because it's all snowy here, but nevertheless, there's supposed to be a beautiful full moon this evening, and we can see it from, no matter where you are, when it's your nighttime, you can see that full moon. What explains that? Does the moon have a light source? Why do we see a moon, right? Those are phenomena. That's what scientists try to do, explaining phenomena. A critical aspect behind phenomena, behind explanation, is it really gives priority to evidence. And this is so incredibly important today. It's not just that someone says something. It's that that person has strong evidence to support their position. It's also critical for building usable knowledge, right? So if we engage kids in actually constructing their own explanations, not us giving explanations to the kids, but our students actually developing their own explanation, this is how they build usable knowledge. It also promotes a really important, promotes an image of science is figuring out what the world is. Often, many students have this image of science as only a body of knowledge. That, yes, science does have a body of knowledge, but that's not the important thing behind the science. What science is all about is figuring out how the world works. And when kids write explanations, that's what happens. They figure out how the world works. So it really promotes a different image of science, and it enhances the nature of science. Kids, learners understand that when scientists make claims, they have evidence behind it. And this is such a critical aspect. So it improves the image of science, and it also really fosters a understanding of what the nature of science is all about. And lastly, it really fosters deep understanding of science concepts, scientific ideas, and scientific practices. Okay, so that is sort of a little bit of an introduction. And now we're actually going to engage in doing a little bit of science. I'm just going to stop here just for a second. And I'm just going to ask if anybody has any questions on any of that introductory material. Feel comfortable to chime in or write a chat. Okay, without seeing anything, I did my, I always count to 20 to see if I get any questions. I did my counting, no questions, so I'm going to move on. So we're going to engage in doing some science. I just want to mention that what we're going to do today actually comes from some curriculum materials. Unfortunately, these curriculum materials are not open source. Everything else that you'll be using does come from our open sources. You can certainly you can certainly modify what I give you today to use, but that's not the purpose. The purpose today is to help you understand what explanation is. But all the material I gave you today, feel comfortable to modify them. I was the lead designer of these materials, so it's not any issue. Okay, so we're going to engage in doing some science. And this is really an important screen because I obviously can't engage you in the whole the whole unit. And so I'm trying to, and because we all have a science background, I'm just going to sort of bring you up to speed about where the students are. So through the unit that they've been studying, and there are 7th grade students. And so from 6th grade and what they've been studying in 7th grade, they know the following ideas. They know that matter is composed of atoms and molecules in constant motion. That they know that. They know that substances can exist in a solid, liquid, or gaseous state. They know that substances have characteristic properties that can help identify substances and distinguish them from one another. The properties that they know are solubility, density, melting point, and odor, and that these can identify one substance for another. And they've been doing some investigations in their classroom as far as realizing that certain things have certain properties. And so they know that baking soda, road salt, and powdered sugar are all soluble in water to a certain extent, right? But in the most part, they're soluble. And the students figured that out in some previous hands-on experience that they had. Now, as we go forward, and this is really important as you write your own scientific explanation, at this point in the curriculum, the students do not know what a chemical reaction is. They know that matter is made up of atoms and molecules. They know that matter has characteristic properties, but they do not know what a chemical reaction is. That is a critical point moving forward. So we're going to talk a little bit about scaffolding scientific explanations. And the reason why is that if we're really going to engage students in complex tasks, like writing an explanation or like modeling, we really have to provide structure for them in doing so. Otherwise, students won't be able to complete the task. So, for instance, if you can think about riding a bicycle, I hope this is true in the Asian countries. I'm not sure if it is. You can sort of tell me if it is or not. But in the United States, as parents, when we're trying to get our children to ride bicycles, we always put these things on called training wheels. And training wheels actually helps the young child, actually balance on a bicycle. Otherwise, they'd fall right over. So training wheels are a scaffold to really help kids learn how to do this difficult task of balancing on a bicycle, 2 wheels. And of course, as parents, and we always take off the scaffold, the training wheels, and the kid can then ride on just 2 wheels. So that's an example of a physical scaffold, right? So as humans, we're always trying to provide scaffolds to help people do tasks that they would find challenging and they couldn't do without the scaffold. Same thing is true with explanations. If we want to get kids to really write good explanations, we really have to provide scaffolds, and hopefully we can release those scaffolds, and then students are going to be able to write the explanation on their own. So scaffolding really helps make the science thinking explicit to students so they can really facilitate and use those strategies like writing explanations. And they also really help reveal the underlying tacit framework of what really goes into writing a scientific explanation. So what is a scientific explanation? It's a discussion, argument of how or why a phenomenon occurs and the conditions and consequences of that observed event, right? So we're going to give you a framework for writing scientific explanations. And this in many ways is the scaffold. And so we're going to break it down into several parts. The first part is a claim. Whenever you write a scientific explanation, you're actually answering a scientific question. So why is there a full moon? Why does something fall when I let it go? So you're answering a scientific question, and importantly, a claim relates one variable to another variable. And we'll illustrate that as we write an explanation. But you're not just making a statement. So you can think of a claim as a statement relating one variable to another variable. But the important thing, as I said about scientific explanations, is they're evidence-based. You have to have evidence. So scientific data, you have to have scientific data that really supports the claim. And you also have to have appropriate, does it really fit? And of course, when we're working with young learners, this really becomes important. So evidence isn't Johnny says that, or right? Evidence is really strong data that you gather by doing an investigation. So you need appropriate scientific data, but you also need sufficient. One piece of evidence typically doesn't work, right? You need more than that. And that's the whole process of doing science, is gathering more and more data to really support your claim. And then the last part of a scientific explanation, the way we're scaffolding it, is that students actually have to have reasoning. What is reasoning? Reasoning provides a justification that shows why the data that I collected counts as the evidence to support the claim and includes appropriate scientific principle. Right? So we want to blend in what we know to say, why is this data actually evidence to support my claim? And then often, as scientists, we want to try to rule out other alternative explanations. Now, one of the reasons why we've actually used this framework very successfully for many years to really support kids and really writing good scientific explanations. And then our next session, I will, maybe not the next one, but sometime this week, I'm actually going to try to show you some explanations that students actually write. One of the reasons why we actually have this breakdown is when I first started writing, trying to get kids engaged in writing explanations, I would say, write an explanation, and you'd get a one-sentence answer. And of course, that's not a scientific explanation. So we had to come up with, what is it that scientists do when they write an explanation? And they always make claims that answer a question. They always have evidence, and they always have their reasoning. In many respects, every journal article, any scientific journal article, actually is an explanation, right? It's the scientist raises a question. They then answer that question using evidence and reasoning. In many respects, this is adopted from Tolman's model of argumentation. So here's another way of looking at it. We always start with a question. That question leads us to designing an investigation. Remember how I said scientific practices always work together? So I ask a question, a scientific practice. That leads to me conducting an investigation, another scientific practice. That leads me to collecting data. I then bring in what I know. I bring in my scientific ideas and my understanding, and I say, which of those pieces of data actually serve as evidence? That's analyzing my data. And sometimes I rule out some of those ideas. Some data might not serve as evidence. It's inappropriate. It doesn't really respond to my question. That then leads me to make a claim. And it might also lead me to get rid of some other ideas, right? It's not the other idea because there's no supportive evidence and reasoning for it. And of course, we get debates in science when the evidence on one side of one claim is not as strong as the evidence on another side, right? So when you get debates in science, when the data isn't really clear, the evidence we have on either side doesn't really support what's going on. That's the whole process of doing science. That's why I said below, above, one of the important aspects of kids actually engaged in writing explanations is all of helping them understand the nature of science. And this is what you see in front of you. It's all scientists is based upon asking questions about nature, collecting data, saying which of that data can really support my claim and other data not. And then of course, showing that other claims aren't as strong as my claim. Okay, so now we're actually going to dive in and do some work. And what I'd like you to first do, just for a couple of minutes, just to make sure to see the breakout rooms work, because we're actually going to also go in the breakout rooms to actually write explanations. I would like you to go into your breakout rooms. And Brunine, we can set up breakout rooms, right? I hope. I mean, hopefully we'll get in the breakout rooms. Yep. So we're just going to go
How
in
many
for,
rooms?
I think they can go in by, I would put them in by their countries, right? Have them all work together. I think that's a good idea. That's what I would do. I would have them work in their country groups.
Okay, let me try.
And or we can mix and match too. But the first thing we want to do, and this is just going to be short, is what do you think might happen when you mix? Again, now we're back being scientists, and there's actually a work in the materials I gave you. So I'm going to just pop out of this. I'm going to stop sharing for a second. In the materials I gave you, and I'm just going to go pull those up. So you might, as you're in your breakout rooms too, you might want to just pull these up. So I'm gonna share my screen with you again. Okay, so one of the handouts I gave you is this, and you can you want to just read the purpose of what we're doing, right? That's gonna that'll help you with the question, right? So what happens to properties when I combine substances? So in this investigations, you will make observations, then you will and then we're going to continue from that, right? So the first thing I want you to do is I'll stop sharing that. And then so you want to make sure you pull that worksheet up and you have it in front of you, because you're going to need it to follow along with me when we get to the next step. So then I'm going to share my screen with you again. And you and your groups want to talk about what do you think might happen when you mix substances together with other substances. And I'll just give you a couple of minutes just to talk about that. Just let's just make this breakout room just 2 to 3 minutes. But let's break in, see what happens, and we'll come back and we'll just have a quick chat. Okay, so into our breakout rooms.
Yeah, I already opened the breakout room by country, so the participant can choose to join in each group.
Okay, we join by the country.
I'm not sure how many countries we have for today. So I set up 6 countries, and for room 7, it could be mixed country.
So there is so while you go in the breakout rooms, again there's a question on the Zoom. I'm gonna quickly try to look at the video, so I'm gonna have silence everything and then see what it says.
One simple but brilliant trick to heat your home in 90 seconds and save thousands of dollars on your heating bill this. Hello, YouTube. One of the most significant aspects of science is explanation. Science doesn't just involve making predictions, it also offers explanations of phenomena. And this has seemingly given us a very deep understanding of how the world works. Today, we're going to examine in some detail what's involved in giving a scientific explanation. What criteria must good scientific explanations meet? So as a preliminary point, it's worth clarifying what is meant by explanation. The term explanation covers many different things. We can explain how to do things, such as how to drive a car or how to use a computer, or I might explain the meaning of an artwork. Scientific explanation, however, is concerned specifically with answers to why questions. We want to explain why things happen. Why did the dinosaurs go extinct at the Cretaceous-Tertiary boundary? Why is it that planetary orbits sweep out equal areas over equal intervals of time? Why was the Spanish flu of 1918 so much more deadly than other flu epidemics? So it's answers to why questions. So that's the general problem that we're going to be focused on. Now, this video concerns scientific explanation, but we might want to keep in mind the question of, is there actually anything special about scientific explanation? After all, non-scientists also explain plenty of things. I might explain why Frank is angry by saying that his car has broken down, or I might explain why the cake didn't rise properly in the oven by saying that you used the wrong kind of flour. These look like perfectly adequate explanations, but they're not scientific explanations. Of course, we're going to focus specifically on the scientific case, but it's just, it's worth keeping in mind that maybe we want the theory of explanation to apply to non-scientific explanations as well. So today we're going to look at what's called the deductive nomological model, which was proposed by Carl Hempel. In some ways, this is maybe not a good place to start, because I think this model is actually quite counterintuitive. But this is really where serious philosophical analysis of scientific explanation begins, so we have to start here. Now, one of the most obvious features of many explanations is that
We should probably bring them back from their breakout rooms.
Okay.
Okay, I think we're mostly back, so I'm gonna just start talking again. There was a question in the chat about how is my version of scientific explanations different than this one that someone found on the web that had to do with deductive nomological scientific explanations. It was 20 minutes long, so being 20 minutes long, I couldn't watch it. I did listen to the first 4 minutes. I would say at least in the 3 or 4 minutes I listened to it, it did talk about explanation, scientific, and it was very clear that there's all sorts of explanations. We always explain lots of stuff, and that's a really important point. You don't want to confuse a scientific explanation with explaining, how to turn on the computer, right? So we use the term explain in a lot of different ways. Sometimes it's helping someone understand the process for how something occurs. But a scientific explanation is different. What I've tried, and again, I'm not a philosopher of science. I'm basically an instructor, right? I focus on how do you support kids in doing things. And so the method you see in front of you, the idea that we broke an explanation down into these 3 parts: claim, evidence, and reasoning, but always focusing on answering a scientific question about why something happens. That's very consistent across what I just heard on this video. And again, I don't even know who this person is, so it's a little hard for me to evaluate it. But scientific explanations always focus on why something happens, and they're always based on evidence. And they're very different than, let's say, how we explain things that happen every day. And unfortunately, as educators, we always use the term explain X. That's also very different, right? A scientific explanation really says, why does this phenomena occur? Do you have evidence for supporting the claim that you're making? So I will further look at that video and see if I can add some other reflections, but we'll talk about that next time. So with that, I was curious, you could either say something or write a note in the chat, but in your groups, what do you think might happen when you mix substances together with other substances? Any ideas?
Okay, yes, Joe. From our groups, we have already discussed related to first questions. What will happen when mix substance together? The first, when we mix a solid with solid, we can know that maybe nothing's happened, only physically mixed, or as a mixture, maybe like sugar or your example like sodium bicarbonate. And then when we put solvent, it will be mixed, and then a chemical reaction happens. So the second questions. Okay.
Go ahead.
Yes, okay. New substance are formed, we can see when it form gas, or there is an increasing of temperature of that substance when it mix, or a decreasing temperature, or color change. So that's the students, and we know when something or new substance are formed in chemical reaction. Thank you.
Right. So sorry, I don't know why my thing keeps jumping around. I can keep my hands off the keyboard. So we also have a comment in the chat as well related to this. So thank you very much for your response. So sometimes when we mix things together, nothing happens, right? That's what we heard. But sometimes when you mix something together, something does happen. And as scientists, we like to call that a chemical reaction. And of course, one of the reasons why we know that happens is because we see indications of it. Yeah. We see color change. We might see smell. If we really want to provide evidence that in fact something changed, then we have to have strong evidence, like the properties of the initial stuff are different than the properties of the new stuff. So we're going to use those ideas going forward to write an explanation about a phenomena that you're going to observe. But again, I'm going to, right, so we're going to now get involved in an investigation and see what happens. So we're going to, in your handout, I provided you this handout.
Mhm.
You do have this data table, and I would like you to fill in your data table. And of course, if this was really my class and we had, we had several days to do this, then we would engage in various different processes. But right now, what we're just going to say, we know that sodium bicarbonate is soluble in water. It was originally a white material. We'll see this as I'm going to actually play the video, and you can fill this information in. But you should find this table on your worksheet, and you can fill it in as we go. So what happens when I mix substances together? We're going to complete this investigation. We're going to do some discussion, and then you're going to write an explanation. So I'm going to play this video for you. We're going to take about a table. And I'm basically mixing together those three. I'm basically describing these three substances to you. And yeah, I'm going to these three substances to you, and then we'll watch the chemical reaction. I'll stop somewhere a couple of times during the video to see if you have any questions. What's really important, you have to let me know if you can hear the video. We're going to take about a tablespoon of calcium chloride. And when we look at calcium chloride, you can see that there's little tiny grains in there. We're also going to take about a tablespoon of sodium bicarbonate. And when we look at the sodium bicarbonate, we also notice that instead of having little grains, it's very fine powder. Lastly, we're going to take about a tablespoon of powdered sugar. So sort of a level teaspoon of powdered sugar. I'm going to put it inside my. Everybody can hear that? Okay.
Yes.
Yeah. Okay. Going to keep going. We're going to take about a tablespoon of calcium chloride. And when we look at calcium chloride, you can see that there's little tiny grains in there. We're also going to take about a tablespoon of sodium bicarbonate. And when we look at the sodium bicarbonate, we also notice that instead of having little grains, it's very fine powder. Lastly, we're going to take about a tablespoon of powdered sugar. So sort of a level teaspoon of powdered sugar. I'm going to put it inside my bag. The question we're trying to answer is what happened when we mix things together. And one of the things we're going to mix this powdered sugar now with my. Okay, so I'm going to just stop just for a second. And one of the things in completing your table, so we now know that sodium bicarbonate, calcium chloride, and sucrose are all soluble. We did that before. We also know that sodium bicarbonate is a white powder. Calcium chloride is kind of more of a granular white substance, as is sucrose, right? We just saw those observations, and now we're going to record our observations of what happens when we mix these things together down here. So I'm going to you should be recording your stuff, so I'm going to keep playing the video. We're going to take about a tablespoon of calcium chloride. And when we look at calcium chloride, you can see that there's little tiny grains in there. We're also going to take about a tablespoon of sodium bicarbonate. And when we look at the sodium bicarbonate, we also notice that instead of having little. Sorry, I'm going to move ahead a little bit because I didn't realize it started over. Is what happened when we mix things together. And one of the things we're going to mix this powdered sugar now with my calcium chloride. And of course, when I put those two things together, and I ask myself the question, what happens when I mix those together? Nothing much happens, they just mix together. I'm going to take the sodium bicarbonate,
And I'm going to add that to my plastic bag. When I mix all three of those things together, once again, all I did was just mix them together. Fill this little container about 3/4 full of water. Do is I'm going to very carefully put it inside the bag, and I don't want to spill it, but I do want to seal this bag. So I'm pretty comfortable that this is all.
So we basically now saw that all three of those substances, when we mix them together as solids, nothing much happens. They just stay there as solids. And now I've added some water, and I flatten the bag, and I'm sealing the bag now, and we'll see what happens from that point forward.
Sealed is I'm going to turn the water, this little container over so that the water spills out of the bag. And once I do that, I want you to now make a prediction what might happen when I do that. So the bag looks very different than it did before. It's now has filled. It's now has expanded, and we can ask ourselves a question: what might have caused that to happen? So again, I want you right now. I'd like you to answer that question about what happens when I mix things together, and I'd like you to write a scientific explanation related to that. Now, notice that it's very puffy, and of course, it's not like an unfilled bag. The other bag looked something more, a little bit like this, right? So you can see the difference in the two bags. And so the question becomes, what's inside that bag? And we might say that, oh, gee, maybe it's got filled with a gas. And then we could ask ourselves, well, what kind of gas might it be? And we might say to ourselves, well, the gas might be oxygen. Could be an okay prediction. And of course, if it was oxygen gas and I took a match and I would put it in there, the match would probably glow brighter. We might also want to take a guess and say, what's inside that bag is hydrogen gas. And of course, hydrogen gas, and I put a match inside it, then I would expect to see an explosion with the oxygen reacting with the O2. But perhaps it could be some other predictions you might want to make. What else might this be? And perhaps it might be carbon dioxide. And of course, if it was carbon dioxide, the flame would go off. Nitrogen, the same thing would happen. It would not support combustion. If we looked at my products that I began with, powdered sugar, which is C6H12O6, and sodium calcium chloride, and of course then sodium carbonate, there is no nitrogen in any of these, so this possibly can't be nitrogen gas. You can see here that I have a burning piece of wood, and my assistant here is going to open this bag up, and I'm going to put it inside the bag, and you'll notice as soon as I put it inside the bag, the flame went out. Now, I suppose we should try it with another bag, just to show that this works. Could you inside this bag, you'll notice it doesn't go off. And could you open this bag up again, please? Open up this bag again. Voila, it still goes out. This is the white milky material that formed when I mixed the sodium bicarbonate, the calcium chloride, and the powdered sugar. And you'll notice that there's beginning to be a separation. There's more of a clearer liquid. It's cloudy, but it's much clearer than what's on the bottom. And so it looks like I've formed actually a precipitate. Also know from our previous work that baking soda, sodium, calcium chloride, and sugar are soluble.
Okay, so there's the experiment. The question was pretty clear. What happens when I mix substances together? I mixed these three things together. I mixed baking powder, sodium bicarbonate. Baking powder, which is sodium bicarbonate, calcium chloride, and sugar all together. When I did that, nothing happened. But when I added water, something very interesting happened. the bag became very puffy, filled with got filled up with a gas. When I put a match inside that bag, it actually extinguished the flame. I did a little bit of a control experiment showing it when I just put it inside a bag, the flame does not go out if I just put it inside a normal bag, but in this bag, they put the flame out. We also notice now at the end of the experiment investigation that in fact, there is a white powder, a white milky substance that we call it a precipitate that actually formed, and there's a clear layer above it. And of course, we know that the three things that I started with were insoluble. So what I'd like you to do now,
We're gonna take about a tablespoon of
what I'd like you to do now is we're going to actually go into our breakout rooms. And I'm going to give you a little bit of time to do this because I want you to come back with a written scientific explanation. And I want you to talk to your group about what you observed. Let's make sure that every breakout, you can certainly go and work in your team, your country teams. But if you don't have any partner, you really want to go into another room. So we can make a couple of different rooms. So make sure there's at least 2 or 3 people in a room so that people can talk to each other. You want to write a scientific explanation about what happens when I mixed those substances together. And remember, I want to see a claim. Remember, a claim answers the question. And it not only answers the question, it actually relates one variable to another variable. So think about that. 2, you want to make sure you provide your evidence. And 3, you want to make sure you give you want to make sure you say why the data that you collected actually counts as evidence. And you can use the information that we've already learned as students our background knowledge that I brought up before. You can sort of look once again. And so I'm going to give you about 10 minutes to do this. Then I'm going to have us come back and we will share. I'm going to ask one or 2 groups to present, and we will critique those. And then based upon the critique, we'll go from, we're either going to go in the further breakout rooms to rewrite our explanations, or we'll move on. So that's what we're going to do right now. We're going to go into our breakout rooms. You're going to write a scientific explanation, a claim, evidence, and reasoning. And then we'll come back and we're going to discuss them. Any questions or comments? Okay, without any questions or comments, let's go into our breakout rooms. I will see you back in this main room in 10 minutes at 15 past.
We're gonna take.
Hi, I think we're all back. At least that's what I can tell. I hope you guys made progress on writing your scientific explanation. And so what we're going to do now, which is a critical part of classroom work, right? So what we're trying to do is to help kids write explanations. That's why we broke it down into claim, evidence, and reasoning. And hopefully, once students write a number of explanations, we don't have to do that anymore. So that scaffolding is a critical part of classroom instruction, of writing scientific explanations, but so is critiquing and revising explanations. We always want to be able to share our work with our classmates. And then based upon the feedback we receive, revise them. And so what I'd love to happen right now is for a group to share their explanation and very clearly state what is their claim, and the rest of us listen to it to see if we want to provide any feedback. So I'd like the group to first say what's their claim, and then see if there's any feedback, and then what's their evidence, receive feedback, and then reasoning, receive feedback. And then we can all talk about it. And if there's time and there seems to be a need to rewrite some of our other explanations, we will. But right now, I'd like us to critique at least one group's explanation. So who's going to come forward and for their group and tell us about their explanation?
Okay, maybe I will go first, Professor Joe.
Okay. And where are you from, and who are you? Say who you are and where you're from.
We are from Indonesian group.
Okay. Sounds good. Okay, so let's hear your explanation.
We will trying for the explanation from the claim. And for the claim, when the sodium bicarbonate, sugar, and calcium chloride mixed together is from a chemical reaction that is form new substance. And for the evidence is the container, it's explained filling with the gas. And for the explanation is when you put the match into the container yeah, put the match into the container, it will where is it? Gold. The fire is gold. So this is claim that the gas that produces is CO2, not hydrogen or nitrogen.
Okay. And so your claim was when a chemical reaction occurred, new substances were formed.
Yeah.
And then your evidence was that there was a gas, there was a gas in the bag, and then it put out the flame. It extinguished the flame, right?
Yes.
Okay. And your reasoning, what's your reasoning?
And the reason is because there are possibilities what the gas produced from hydrogen or nitrogen or carbon dioxide. The evidence that makes sure that the gas produced is carbon dioxide. When you put the match, the fire will go out. So this is the evidence or the evidence or the reasons why the produced gas is carbon dioxide.
Okay, so we're pretty convinced
Yes.
that that's pretty solid evidence that in fact something happened, right? That
Yes.
gas wasn't there to begin with, right? So we can say we know something new was formed because we now have this gas that will put out a flame. I want to hear from other people what they their comments on that explanation. Yeah, there's a comment in the chat that says it's hard to understand without reading. And I understand that, but and we could have shared, except I wasn't sure how fluent everybody was in writing English. So I didn't necessarily want to spend time everybody writing an English explanation right now. I can certainly type it. Well, can everybody follow me? And that's why I tried to repeat it. So hopefully that was okay. So the claim is a new substance was formed, and the evidence was and the evidence was that the bag filled up with a gas, and that gas was able to extinguish a flame. And so it's likely that the gas that was formed was carbon dioxide. And I wonder if there's any comments that other groups would like to give on that explanation. Yes, I can stop sharing my screen. And if people want to share their screen, they can, if they have a written explanation.
Can I try? Can everyone hear me?
Pardon?
Can you hear me? Can I try? Can I try on the explanation?
Can you repeat that again? I didn't hear it. Someone said, can I try? Yes, please go ahead and try and share your screen and give us an explanation.
Hello.
Okay, Gareth, this is a written one. Let's see what this,
So I agree up to this point where I agree up to the statement that the new gas that was formed was carbon dioxide. To me, for example, to me, I'm a physicist, so I'm not quite sure the property of the gas. So what I think, to me, I have to make sure that the substandard form is new by comparing to what I know. So I compare the property of these four substances: the water, the calcium chloride, the sucrose, and the sodium bicarbonate. And these four substances, if it could turn into gas, their gas could not extinguish the fire. And that's why I think that there must be another piece of evidence or another piece of reasoning by comparing the property of gases of these four substances. If they could turn into the gas states, and make sure that these four will not extinguish the fire. Does it make sense?
so I wasn't able to get all of that. You're breaking up, but I will try to repeat it.
Let me type in the chat. I think
Chat. I don't have it in the chat. Let's see. I don't have the chat open right now.
type it.
Okay, so I think I heard you say, and I could be wrong, that we need to have more evidence about what's going on. And We could debate that if we like, and unfortunately, we're not here face to face to debate that. But we know that there was no gas to begin with, and then we had a gas. We also know that calcium carbonate, sodium carbonate, calcium chloride, and sugar are all soluble in water. And at the end, we saw there were some things that weren't soluble in water. So we also have other evidence here as well. So to the evidence that it put out a flame, that it created a gas, and the gas put out a flame, I would add, we also have a substance that's insoluble in water. So we have at least 3 pieces of evidence, right? Which should be sufficient. We know that we didn't have a gas to begin with. We now have a gas. That gas could put out a flame, and we also have we also know that we formed a insoluble substance. So those are 3 strong pieces of evidence. I wonder if I could see your reasoning. Could you, who's ever sharing their screen, if they could share their reasoning? No reasoning. So I'm going to now, I want to thank you very much. I'm now going to tell you the most challenging part behind any scientific explanation. And it doesn't matter what grade level you're working at. If you're working at middle school, high school, or college, the most challenging part for any student is to write evidence. I'm sorry, reasoning. So I would say that that in this particular case, our claim should be that when I mixed the 3 substances together, I formed new substances. Now that's a really important idea, because a claim always relates one variable to another variable. If I just say new substances were formed, that's not relating one variable to another variable. So if I was trying to give a student feedback, I would say very clearly, please relate one variable to another variable. Then we have our evidence. And our evidence is that as I said, we formed a gas, the gas put out a flame, and we now have an insoluble substance. That's evidence. That was our data. Now, what's the reasoning? The reasoning says, why is that data puts out a flame, a gas was formed, and there's a solid at the bottom? Why is that? Why is that data evidence? And I would say that the scientific reasoning behind that is that those properties are different than what was in the original stuff. The original materials did not have a gas, right? That a new material was formed that has different properties than what was there at the beginning. That's the scientific reasoning, that I now have new substances that have different properties than what was there in the beginning. And I know, right, that properties can identify substances. That's the scientific reasoning. So that's what we want to try to push our kids to have them explicitly say, I know I got new stuff because my data shows me that it has different properties than the original stuff, and we know that properties can identify substances. So that's a really critical aspect. So you want to really push your students when they write explanations to make sure they have all 3 parts. A claim, when I mix the 3, I'll write it out for you. Let's see here. Okay, so what's my claim? My claim would be when I mix the three.
Excuse me,
Actually,
may we see your screen?
Oh, you
Yeah.
can't see my screen, right? Sorry about that. Oh, yeah. Okay, share screen. There you go. Right, everybody can see that? Yep.
Yes.
When I mix the four substances together, right? Because one of them was water. That's my claim. And the reason why it's my claim is because I'm relating one variable to another variable. My initial materials are different than my final materials. Right? What's my evidence? A gas was formed that extinguished a flame. And then two, a solid substance was formed that did not dissolve. My reasoning, new material was formed that has different properties than the initial materials. And I know that when I know that different substances have different properties. So that would be my scientific explanation. Now, this is let's say one of our first scientific explanations that the children would write, the students would write. As time goes on, I'd want to take that scaffold away and have the students not write claim, evidence, and reasoning, but just write one statement, right? Rather than breaking it up into pieces. But this would be a scientific, a good, very appropriate scientific explanation for a beginning seventh grader. So with that, I'm going to stop and just see, I'll go back on chat. And I'm going to see if anybody has any questions. I see there are some explanations written in the chat. Does anybody have any questions? And again, this is your first exposure to explanations. Anne will continue doing it in water quality. I'm going to do some other work with you as far as the next time, not tomorrow, but I think on Friday morning, I'll do more further work with you on explanations.
So I have question. So
Yep.
why we should put a flame inside the plastic with already show us there is a gas there because what is it, the the size of the plastic being bigger. And if we just put the flame there, then we ask the student to think about what kind of gas are there. Is it correct or not? I'm just thinking about the reasoning should be also add information about what gas inside that created the foam.
Right. So it's not, so in this unit, as of this part, we haven't necessarily talked about properties of the gases, right? Although they do know that oxygen supports combustion, but they don't necessarily, they know probably from prior knowledge that carbon dioxide puts out a flame, but that isn't essential. What's essential is that there's now a gas that puts out a flame. What's it called doesn't matter, because remember what the question we're answering is what happens when I mix substances together. And the response is, when I mix these four things together, I got some new stuff. How do I know that? Well, there was a gas that formed that wasn't there to begin with. That gas has a property of putting out a flame. That wasn't there to begin with either. Air does not put out a flame. The air causes things to burn, the oxygen in the air. And then the third piece of evidence is actually that I have this solid at the bottom. Now, if you're in high school, you probably want to go farther, right? You can identify the substances. But this is a 7th grade unit. And at least in the United States, they don't have to do that, right? So the reasoning just is that I have new stuff with different properties, and I know when I have different, and I know that I have these different new substances because properties will identify substances, and that would make a perfectly clear, appropriate explanation. But again, as teachers, you have to decide what really works for you in your school. I'm just trying to give you a basic format for what an explanation looks like. That's right. Evidence in the chat, it says reasoning linking evidence to claims. That's absolutely correct. Peter also wrote a question about, so we as teachers have to literally convert the language for modules we have learned from English to unless there's that's a question for Kessera or Buren to answer. I don't know that. All I know is I can give you these units in English. They are in Spanish for the most part, but not in they're actually in Chinese as well. Do we have them in Chinese? No, we don't have them in Chinese. We have them in Spanish. So I don't know how to we don't have and they're open source. So if you want to use those other materials, you have to convert them yourself. Okay, I'm gonna move on. And I'm gonna move on. And I'm gonna let's see, I'm gonna do this now. So I want to quickly examine what we did. And I'll have to talk through this a little quickly because we are running out of time. So I want you to think about what we did. So when you constructed a scientific explanation, in order for us to do that, what did we have to do? Well, we did an investigation, right? That's a scientific practice. We conducted an investigation. We analyzed data. we wrote an explanation. In 4, we shared our explanations. We communicated. Those are all 4, and there could be others as well, but those are all 4 practices. And the reason why I'm bringing this up is just to stress the point that whenever you write an explanation, you're also always involved in other practices. So we use these practices of we conducted an explanation, we analyzed data, we wrote an explanation with a claim, evidence, and reasoning, and we shared our explanation, our 3 critical practices. And we use that along with our prior knowledge that properties identify substances to make a claim that new substances form that have different properties from the starting materials. And what's interesting is that this is the definition of chemical reaction at the macroscopic level. The kids did not have to know that. It was through their own investigations, through their own inquiry, that students, you, others are able to make sense that when I mix things together and I form new things, as scientists, we label that a chemical reaction. So that's a really important aspect, because often we want to just tell kids what a chemical reaction is, rather than in having them through their own investigations figure it out. And in this case, this allows kids to figure out what it is. So we supported kids in constructing an evidence-based scientific explanation if a chemical reaction occurred based on the properties of substances before and after the substances interacted. This is just for you. If you want to know what happens, this is the chemical reaction that occurs. It's a fairly complex chemical reaction. The sugar was just a thing on the side, right? It was just to confuse people, right? The sugar had nothing to do with the chemical reaction. The water is simply a medium, right? So it also is not actually really involved in the chemical reaction. It's there as a medium that allows it to happen. And the sugar is simply it's a distractor. And one of the reasons I put it in there is if you look at the handout I gave you, so I'm going to go back to that handout. If you look at the handout I gave you, and you go to the bottom, it says here, what new questions did you have? And hopefully some of you saw that and asked it. I always like, when I do investigations, I always like asking kids or have kids experience a phenomenon. I always say, what questions do you have? And hopefully some kid is going to ask, were all 3 things necessary? And then if all 3 things are necessary, then you can go on and you can look at this next one, which is basically ruling out or figuring out if all 3 things are necessary or not. So you can look at this and you can take it actually further and actually doing another practice, which is actually having kids design an investigation. I basically designed that investigation for you, but this one, based on what I did, then you are to design your own investigation. So again, that was another type of a scaffold. I modeled how to do something, and then I'm asking you and your group to do an investigation. Yeah, there's a interesting comment in the screen. It says, can I disagree with you? I think it's hydrogen gas and not carbon dioxide. So I believe we need to test the gas with lime water. If it's carbon dioxide, you can certainly go ahead and test it with lime water. That's really great. One of the things I will let you know is what happens when we put a match with hydrogen gas. Anybody know? A flame with hydrogen gas is what?
Explosion, maybe.
It
I'm
explodes.
not chemist, but I think explosion.
Yeah, it's an explosion. In fact, all the kids kind of know that that hydrogen gas causes an explosion, and they hope it's going to be an explosion, right? That's what they want. They want to see an explosion, but it's not an explosion. So it can't be hydrogen gas because hydrogen gas will always cause an explosion. And if you have those kind of I kind of love this lab for you can do all this stuff, right? All these ideas that we could use lime water to see if it's carbon dioxide. We could actually take some hydrogen gas and we could see what happens with, we could take some known samples of hydrogen gas, carbon dioxide, a nitrogen gas. In all three of those situations, we could sort of see what happens when you put a flame in there and see what happens, right? So, and then we could say, okay, in this particular case, it didn't cause an explosion like what happens with hydrogen. It caused the gas to go out. So it's got to be carbon dioxide or nitrogen gas. Of course, none of the substances have nitrogen in it, so it can't be nitrogen gas. It's got to be carbon dioxide. It could also be oxygen gas. But when you put a flame inside oxygen gas, pure oxygen, it just causes it to burn brighter, right? So we could test all three of those gases, or all four: carbon dioxide, hydrogen, nitrogen, and oxygen. We could see what happens. And I think that's a really nice addition to the lab. And I also think it's a really nice addition to try this lime water. No one's ever suggested that before. I think that's a great little addition. I'm going to go back and share my screen with you and wrap this up for today. So one of the reasons I really love scientific explanations is because it really helps kids build a scientific disposition. And for me, one of the big aspects between a scientific disposition is saying to myself, do I have enough evidence to support my claim? And it also helps kids wonder and to ask other questions. So to me, engaging kids in explanation really promotes a really important scientific disposition. One, always asking, do I have enough evidence? Two, asking for further questions. So to me, that's a really critical aspect. I'm going to hopefully encourage you guys to do explanations in your classroom, because just imagine if we started to build explanations in the elementary school, and then from elementary school, we move over to middle school and then high school. Students will become much richer in understanding what science is all about and understanding the critical aspects of what evidence has to do in writing scientific explanation. I had a wonderful experience actually just about 3 weeks ago. I actually had a visitor from Japan that wanted to see a school in the United States actually doing science. So I took him to a school close to East Lansing where I live. And we went to the classroom, and the school was actually doing, just coincidentally, I have to tell you this, I was so surprised, the same experiment I showed you today. And of course, the scholar from Japan really enjoyed this experience. But the teachers told me afterwards, when we were in the discussion, that that today it's much easier to have kids write an explanation than it was 5 years ago, because now they see kids coming from grade school writing explanations, having background knowledge in explanations. And so they don't have to worry as much as teaching all the parts. Yes, you still have to critique it. You still have to work with kids to really get them to do that reasoning correctly. But the kids come with some background knowledge. So if we can actually, from the earliest ages on, get kids to construct explanations, we will really have a different type of learner than we've had in the past. Okay, I want to just quickly thank Activate Learning, because these are their curriculum materials. Feel free to use what I gave you if you like. Unfortunately, these materials are not open source. In writing explanations, business is not the same. Science education is very different today than it was 5, 10, 15 years ago, even as little as 5 years ago. We really want to get kids involved in the act of creating stuff. In this case, the act of creation was writing that explanation, because when kids create stuff, that's how they form their knowledge. And its business is not the same, because science is just not a body of knowledge. We actually have to have evidence to really support our positions. And that's what explanations do. Don't worry about that one. So I like to think of today as revolution, and it's not evolution. Science education is very different today. And with that, we have about a little bit of time for questions. I really do want to see if you have any questions related to explanations. And then
Thank
we'll
you for the presentation, Joe. May I ask? So I just want to clarify for myself. So the students should do the explanation based on the data they have collected during the laboratory work. Am I right? So they not necessarily need to prove their or write the reasoning based on some theory. They might not know the theory or write the formula of reaction or something, as we did on our chat.
Right,
do you know what I mean? So yeah, so they should write their reasoning based on the data they have collected, and write the simply with their like a vocabulary or something, right?
Right. So they should write their evidence. They should write their explanation based on the evidence they collected. And the theories and the principles come in to show why that data is actually evidence. Right. So like in our case, that I got a new gas, why does that show that data, that observation is evidence? Well, it's that I have a new substance. The reason why is because it's a new property that wasn't in the original materials. And I know that properties can identify substances. So you bring in the theory, the principles, in trying to very clearly say why that data counts as evidence to support your claim. Does that help? Okay, gotcha. Any other questions?
Hi, Joe.
Hi, go ahead.
Maybe I let the other say it first. Yeah, please.
Okay, I just have a comment from your presentation, Professor Joe. At the first, when I hear your presentation, I think that the revision or explanation that give to the student, it's about the submicroscopic level. Because in Indonesia here, where the prerequisite knowledge from the 7th grade student, it's not enough to do the reasoning that you bring to us here. But it's clear when you explain the explanation about the experiment that you bring to us tonight is not in submicroscopic level, or is it just about the properties of the substance? Is it make all of the presentation is clear? Thank you very much, Professor Chu.
Yeah, you raise a really good point.
Yes.
This is just the beginning, right?
Yes.
So
yes.
this is a macroscopic explanation.
Yeah.
It's not an explanation that deals at the microscopic level. If we were to continue to go on in this unit, that's where we start going into the microscopic world.
Yeah.
And so eventually we want the explanations to say, you know, the atoms of the original materials rearranged to form new materials, right? But that the kids aren't there yet, but they can still write a macroscopic explanation. So you're absolutely, you know, in the US at the 7th grade level as well, we move on to chemical reactions involve the rearrangement of atoms to form new molecules. But that's just, that's a little later on, right? So we're forming a macroscopic explanation of a chemical reaction, and then we'll move on and we'll form what's happening at the microscopic level.
Okay.
Right. My goal today was not to teach science. My idea was to teach what an explanation is. So anyways, I have to pay attention to time because I have to actually run off to my other job because it's the morning here. So I want to thank everybody. I hope you found this somewhat valuable. Please send me emails. Please send me emails if you have questions. There's my email in front of you. Tomorrow, we're not gonna focus on explanations. We're gonna build models, right? So what we're trying to do right now is I'm trying to give you background information so that Anne and Consuelo, dealing with health in her hands, can go into the unit with with you having some knowledge of practices and disciplinary ideas, and particularly the practice of explanation and model building, because we know they're so important in having kids form knowledge. So tomorrow we'll pick up with building a simple model. And then Anne will then present on Thursday again on water quality, building in some explanations. And then on Friday, depending on what happens on Thursday, we'll focus further on explanations. Right now, I'm thinking about giving you a rubric and having you look at a rubric and analyzing some student work. But that might change. So depend on what happens the rest of this week. So with that, I'm going to sign off. I think Kesra has a question. Kesra?
No, I think the last comment that the other gentleman raised, I think it helped me to reinforce that the team that we are forming, right? When we decide a PD, yeah, we should have a team that also consists of the teachers, right? That will also can identify the grade level, disciplinary core ideas, right? That relevant to the grade level, so that the unit that we are adopting will be relevant to the grade level in each country context, right? Yeah, I think that's because the questions about, what do we need to explain about the whether it's carbon dioxide or other stuff, right, that go further. I think it depends on the grade level expectation of the in that country, and I think the teachers in the team will help confirm that. Yeah.
Yeah, I think it's really important for people to realize that I'm trying to give you a perspective on how I see science education is moving internationally based upon my work. But you're in your country, it could be different, and you have to modify, adopt things that really fit what happens in your country.
Yeah.
But what I can say
Mm.
is that I do know that if you really want to get kids to, if we really want to get kids to really build useful knowledge, we have to engage them in scientific practices,
Mm.
right? You have to get kids to ask questions, design investigations, write explanations, critique explanations, use evidence, build models. Anyways, with that, I have to really, I
Leave.
apologize.
Yeah.
I have to get to my other job.
Okay. Yeah. So
So
see
I
you
will see
next
everybody.
time.
Yeah, I'll see. It's tomorrow morning, bright and early at, we're late for you. It'd be my
Yeah.
7 a.m. and I believe it's either your 8 p.m. or 7 p.m. So I'll see
7
you.
p.m. Bangkok time. Yes.
I'll
Mhm.
see you tomorrow night,
Yes.
and I look forward to it. We're actually going to engage in a little bit of modeling tomorrow. So
Mm.
see you then. Bye-bye.
Okay. Yes. Mm.
Thank you.
Bye.
Bye
Thank you.
bye.
Bye bye. See you all tomorrow.
Thank you.
Have a good night and
Bye,
have a
thank
good
you.
morning, Joe.
Good night.
Bye.
See you.
Good
Yeah,
night.
sweet dreams.
Yep.
Good night, everyone.
Good night, everyone. Bye.
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 เป็นทางเท้ายังครับเนี่ย
ทานก่อนมาตะกี้นี้ไปซื้อ ค่ะแล้วบุรินทร์เรียบร้อยแล้วใช่ไหม
เรียบร้อยแล้วครับ
โอเคเดี๋ยวบุรินทร์convert เป็น recording
เป็นครับผม
ใช่
แล้
ไหม
วก็
คะ
ให้มงแปะขึ้นไป YouTube
ค่ะ โอเค
โอเคครับครับสวัสดีครับ
ได้
เพื่อนๆ
ค่ะสวัสดีค่ะ บ๊ายบาย everyone